If there is friction between your object and the ramp, then when drawing your FBD, I recommend saving the force of friction for last. First, figure out what direction the object would move relative to the surface, given the other forces, and then add in that force of friction to oppose the slippage. So suppose here we release this box from rest at initial time, and if there's just the normal force and the force of gravity, we know the box will tend to start slipping down the ramp. Therefore, friction is going to show up pointing up the ramp to oppose that. Now that we've got our FBD, next step, AAA. Here's our FBD once again, and it's pretty much the same as before. The only difference is that we've got this force of friction pointing up the ramp here. I don't know how big friction is just yet. We'll have to discuss that in a moment. Otherwise, the geometry is all the same, and we can state once again these expressions for the components of the force of gravity. Okay, using this to now write out Newton's second law. Okay, x component of Newton's second law. We've got sum of forces in the x direction. There is FGX in the positive x direction, and then friction in the negative x direction opposing it, so minus our force of friction, which gives us this expression right here, since we know that FGX is mg sine theta. Now, at this point, we don't yet know what kind of friction is acting. We're going to have to think about that some more, so I just have to leave this as force of friction. And I have to warn you about a common mistake that is made with an expression like this. There's an m and an m, so there can be a temptation to try and cancel them. But you must be able to factor an expression before you're able to cancel. So, for example here, if you have ab plus ac over a, I can factor out an a from both terms in the numerator, and if I can factor it out, then I can cancel that a with the a in the denominator, all good. However, if we've got an expression like this, where there's an a here in front of the b, but not with the c, there's no a to factor out, then I cannot cancel those a's and cannot simplify this expression to this. This is incorrect. So here I just have to leave this expression like this, because there's no m over here to be factored out. Therefore, I can't factor it and I can't cancel. Okay, so that's my expression for the acceleration in the x direction at the moment. In the y direction, it's the same as the previous video. Normal force is equal to the y component of gravity. One other thing to point out, I emphasized in the previous video that on a ramp, the normal force is less than the weight of the object. And you can really see that visually from this FBD. Here's the magnitude of the normal force, which is balancing the y component of gravity, and this leg is, of course, shorter than the hypotenuse here. So this normal force is shorter than the hypotenuse here, shorter than the force of gravity. Normal force is less than the weight. Okay. Now that we've written these expressions from Newton's second law, use what you know about this scenario here to find an expression for that force of friction. Let's examine and consider this force of friction between the block and the ramp. So you'll have to ask yourself, this begins kind of a thought process that's a bit like a decision tree. Ask yourself, will that object break static friction? If you release it from rest on the ramp, is it just going to stay put? Will friction hold it there? Or will it start to slip? What would start to cause that slippage? Well, it would be the x component of gravity right here, FGX, pulling the object down the ramp. That would tend to cause the slippage. And of course, static friction shows up to oppose that slippage. But is static friction strong enough to oppose FGX? You don't know until you check. You have to calculate numerically. So let's check. Let's find the maximum value of the force of static friction, which we know is mu s times the magnitude of the normal force. And our normal force we've worked out from the trig is mg cos theta. So here, this expression will give us the biggest possible value of static friction. That's as big as static friction can be. But then we must compare that to how big the x component of gravity actually is to see if friction is able to beat out that force of gravity that's trying to cause the slippage. So we need to compare this expression to this. So if you had numerical values, you would calculate this and this, compare the two, and then if the answer was yes, static friction wins, the max force of static friction is greater than that force, than that x component of gravity, then we know that static friction, that the friction that's present will be static friction, and that static friction will be exactly equal to the x component of gravity. It's only as big as it needs to be to oppose gravity. How big is that force of static friction? As big as it needs to be to oppose slippage, and no bigger. So right here, a common misconception shows up, which is that this expression for the maximum force of static friction is not always how big static friction actually is. That's the biggest it can be. But it's only going to be as big as it needs to be. It'll only be as big as the x component of gravity. So then, if it's just able to match the force of gravity, net force in the x direction is 0, acceleration in the x direction is 0, and we remain at rest. I'm going to emphasize once again here that static friction will only be as big as it needs to be. So our free body diagram will end up looking like this, where static friction is exactly as big as the x component of gravity, equal to mg sine theta. That's how big it is. It is definitely not like this. This expression, mu s mg cos theta, that's the maximum force of static friction. That might be too big for our scenario. It can't be bigger than this FGX right here. That would be absurd. It's like placing the box on the ramp and suddenly friction makes the box spontaneously launch up the ramp. Never seen it happen. All right, so that's what we do if we decide that static friction is big enough to oppose FGX. But what if it's not? If instead the maximum force of static friction is less than FGX, then gravity is going to cause the box to break static friction. It's going to start to slide. Then we know if we have slippage, then our friction is kinetic friction, and that can always be calculated with the expression mu k times the magnitude of the normal force. So mu k mg cos theta. If we're slipping, then that's guaranteed to be the expression for our force of friction, which will be kinetic. And our FBD will look like this, with a force of friction, kinetic friction, that is less than FGX. Kinetic friction is generally weak compared to max static friction, so it'll be less than FGX right here. And going back to Newton's second law, we can sub in for our force of friction FFK, which is this expression, put in that mu k mg cos theta in for our force of friction. And looking here, I have an mg on this term in the numerator and an mg on that term, so I can factor out an mg from both terms in the numerator. Factor out that mg, and since I've factored out an m, there's an m in the denominator, those m's can cancel because I was able to factor them out first. Canceling those, we have this expression here for the acceleration of your block down the ramp. Note that before we added friction, the acceleration down the ramp was just g sine theta, but including friction, kinetic friction, this term minus mu k cos theta minus this term here makes the acceleration smaller. Of course, that's friction reducing the acceleration, making it slide more slowly down the ramp. All right, so having been through all that, here is a scenario for you to practice putting together all these skills. We've got a jellyfish that you've just hooked while fishing off of the boat ramp here, and you're hauling it up the ramp. Let's say it's moving upwards with some velocity. So it is moving, the jellyfish is slipping on the ramp. I would like you to draw a free body diagram for the jellyfish as it is hauled up the ramp here. Note that this inclined plane is sort of the mirror image of the ones in the previous examples. So you may want to refer to this image to help work out which angles are congruent to which angles when you get to the next step, AAA. Choose up the ramp as your positive x direction and then break forces into components as necessary. Then 3, write out Newton's second law in component form and simplify that, meaning canceling terms that cancel if there are any, and express everything in terms of just these variables here. You won't necessarily use all of them, but you must get everything in terms of these variables right here. Then, after that part, I would just like to consider, what if you chose down the ramp as your plus x direction instead? Rewrite your expressions from step 3 and show what would change if you just flipped your axis from up the ramp to down the ramp. And lastly, consider what expression for the tension would be required if you're going to pull the jellyfish up the ramp at a constant speed. So what if instead of accelerating up the ramp, it were just moving at a constant speed? find an expression for the tension, again, in terms of just these variables here, but not necessarily all of them. Okay, so that's a bunch of things to do. Pause the video, start working those out, and I'll go over it in a moment. Done already? No, you're not. Keep working. All right. Okay, your FBD ought to look like this. There's that tension pulling up the ramp. There's gravity straight down, normal force perpendicular to the ramp, and a force of kinetic friction, because we're slipping, pointing down the ramp back that way. Breaking that gravity into components, we recognize that this angle up here is the same as theta, the angle of inclination of our ramp, and our FGX and FGY are these expressions using the trig. Note that this is in the negative x direction, and this is in the negative y direction, hence the negative signs there and there. Did you draw your axes off to the side of the FBD? Always include your axes off to the side. Show what directions you're making positive and whether you're tilting the axes or not, so have that drawn off to the side. Then, for Newton's second law, in the x direction, sum of the forces, tension up the ramp minus FGX minus our force of kinetic friction all over the mass. I'm going to pause on that and skip over down to here. AY, of course, is 0, net force in the y direction. Normal force minus FGY is 0, so we have normal force is mg cosine theta as usual. After writing this, you'll want to write an expression that shows what you're doing about the force of friction. It's kinetic friction here, so you can use good old mu k times Fn for kinetic friction to get this expression for the magnitude of kinetic friction, and then sub that back in up here for FFk in the sum of forces in N2L. Subbing that in here, we get this final result for the acceleration of the jellyfish up the ramp. Ft minus mg sine theta minus mu k mg cos theta all over mass. It's tempting to cancel out mass, mass, and mass, but note we cannot because there's no mass on this term. We cannot factor out the mass, so we cannot cancel the mass. It has to stay, and that's our final result, and it is just in terms of the variables given. Note there's no mu s in here because there's no static friction. The jellyfish is slipping up the ramp. 4. If you were to flip the direction of your axes, that would just change the sign on all of these terms in the sum of forces in the x direction. So then if down the ramp were positive, tension would be negative, those two would be positive, and it would change these signs. And then since we're accelerating up the ramp, the acceleration would be negative if we define down the ramp to be our positive direction. Lastly, what if you weren't accelerating up the ramp? What if your velocity was constant? Then that would imply that the jellyfish's acceleration would be 0, implying that the net force in the x direction would be 0. Here are all our terms in the sum of forces in the x direction. That's this sum right here. So that sum of forces would be 0. And moving these two terms, FGX and FFK, over to the right-hand side, we have tension would have to be equal to this sum to pull at a constant speed. I've got an mg on this term and mg on that term. I can factor that mg out to have this simplified final result here. Note this is saying that to pull that jellyfish up the ramp at a constant speed, I've got to overcome gravity, that's the mg sine theta term, and I also have to fight against friction, that's the plus mu k cos theta term right there.